Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems, and in this module we learn how process management is done in the Linux operating system. So, the learning objectives for this module are to understand how process management is done in Linux, to understand about the different categories of the process properties like the process identity, process environment and the context of a process, to understand how fork and clone system calls are used in the Linux operating system. We all know what a process is. A process is nothing but a program in execution. So, when a program is executed, you call it a process. So, in addition to the code what is involved in the program, you have a lot of other things that are involved in a process. So, a process generally comprises of the text, the data, the stack. So, what is text? It is the set of instructions that are involved in the program. Then you have data, which refer to initialized as well as uninitialized global data. Then the stack is used whenever a function call is made. So, whenever there is a function call, a layer is pushed into the stack, in which you have the local variables of that particular function, and the return value, the arguments to be passed to the function are all involved in this stack region. Then you have a set of registers. So, when a process runs, there will be some values that are kept in registers like the PC, which is the program counter. The program counter stores the address of the next instruction to be executed, and then you have the stack pointer which points to the top of the stack, and like this you have a few other values, say like the return values or system calls, which are all maintained in registers. And then you have a set of kernel data structures or the data structures that are maintained by the kernel, like the process table. The process table has got information about all the processes, and it will have pointers to other data structures which are related to the process. You have this file table, file descriptor table, etc., and so on. So, there are many other data structures that are maintained in the kernel and which will have entries corresponding to this particular process, and all these put together form a process. The process model that Linux is using is similar to the other versions of Unix, but there are a few differences. So, we will first review the traditional Unix process model, and then we will see how the Linux threading model is different. The Unix process management, it actually separates the creation of the process and running of a new program into two different operations. So, this creation of process and running of a program does not happen in one call, that is being done by two different calls. So, the creation of process is done using the fork system call. So, the fork system call is used to create a new process, and when this new process is created, it does not mean that this new process should run a new program, but the process which is newly created can continue to execute what the same can continue to execute the same program whatever the parent process was executing earlier, or the process which created this process is called the parent process, and that process would have been running some program earlier. The same program can be run by the newly created process, and say the parent program was executing a particular instruction, and then from where it left, so the next instruction will be executed by the newly created process. So, the newly created process will start executing from the next instruction where the parent process was executing at the time of creation of this particular process. So, here we see that a new program need not be given, but the process can continue to execute the same program as that of its creator or the parent. And if you want to execute a new program, then there is a call which is called exec. There are different flavors of this exec, like exec ve, exec vp, exec le, exec lp, etc., and so on. So, all these fundamentally do one thing, they run a new program by getting that program as the argument, or the name of the executable or the name of the new program that is to be executed is given as argument to this exec call, and exec call will execute that particular program. And for this, just before the executing this new program, it is not necessary to create a new process. It is okay if the process is created long back, and the process while running, it can run a new program at any point in time. And while this new program is run, or when there is a call to this exec, what is done is that a new binary object is loaded into the process address space. I told you that the name of the program to be run is given as argument to this exec call, and this will have a corresponding binary image, and that binary object is loaded into the address space of the currently executing process, or the process that is trying to run this new program. So, the new executable now replaces the old process program, and the new executable will start executing in the context of the existing process. So, under Unix, a process encompasses all the information the OS must maintain to track the context of a single execution of a single program. So, you have a process structure, and the process structure will have all information related to the particular process, or it will have information about all the information about the process which is needed by the operating system, so that it can track the execution of that particular process. But under Linux, the process properties are categorized into 3 different categories. One is the identity of the process, then you have the environment of the process, and then you have the context of the process. So, we will now learn what each one of these mean, and we will see how different each one of these is. So, first we will see about this identity of a process. So, there are different ways in which a process is identified, and the main thing that is being used to identify a process is the process ID. Each process, when it is created, it is given a number or a unique identifier, and that is called the process ID. And this process ID is very much useful when this process has to be referred to by any users or by any other program. So, say if you want to tell the operating system that this is the process which needs to do this way, or this is the process which needs to be handled in a particular manner, then the operating system is informed by using this process ID. So, when you want to make a system call to signal a process or to modify a process, say if you want to wait for a particular process, then this process ID should be given as argument to the calls which are doing these functionalities. And then you have something called the credentials. Each process has got some IDs associated with it. One of that IDs is called the user ID, and then you also have one or more group IDs with which the process is associated with, and these IDs, they determine the rights of the process, the access rights of the process to access system resources and files. And there is something called the personality that is defined only in Linux, which is not actually present in the traditional Unix systems. So, this personality actually is nothing but it sets the process execution domain. So, under Linux, each process has an associated personality identifier that identifies the personality or the execution domain of that particular process, and based on this you can modify the semantics of certain system calls. So, process with a particular personality can behave by a particular manner for a particular system call. So, the semantics of system calls can be modified using the personality. And then we have something called the namespace. So, each process has a different view of the file system. So, this view is called the namespace. Say for example, each process will have a corresponding root directory. The current root can vary from one process to another, or you can have a set of processes which are using the same current directory, and each process can view a set of mounted file systems and so on. So, all these put together form the namespace, and many processes can share a common namespace, and they can operate on a shared file system hierarchy, having the same root directory, having the same set of mounted file systems and so on. and processes and their children can have different namespaces. Say if a process is creating a child, generally the namespace will be inherited by the child process from the parent process, but now the child process can choose to have a different namespace, and hence processes and children can have different namespaces. And now after seeing this process identity, now we will see about this process environment. The process environment is generally inherited from its parent process. As I told you, when a child is created, the child inherits the environment from the parent process, and this environment comprises of two strings. One string is the argument vector. This is nothing but the list of command line arguments that are used to invoke the running program. So, when you are trying to run a program, say if you are running a program in C, say you have an object file, say a.o. So, you will say give say dot slash a.o, then followed by that you will give the arguments which you need to provide as argument to the running of that particular a.o. So, the first argument is a.o is nothing but the name of the program which has to be run. Then followed by that you will have the other arguments that you need to give as arguments to the running of the program. So, all these put together form a list called the argument vector, which is nothing but the list of command line arguments. And then we have this process environment. The environment vector is nothing but a list of name equal to value pairs. You have a list of pairs, each pair is of this form name equal to value, and these pairs will define the different environment variables. Say for example, one such environment variable can be term term. So, you can have term equal to whatever be the terminal. This is used to specify the type of the terminal which is connected to a user's login session. So, very similarly you can set many other environment variables, and this can be given as argument when a process is being run, when a new program is being run. So, this argument vector and environment vectors, they are not altered when a new process is created. So, when you are using the fork to create a new process, whatever is there for the parent process, the argument or the environment will be the same for the new process as well, or the child will inherit the environment of the parent process. But now, when you are invoking a new program using the exec call, then a new environment can be set up. So, there are two flavors of exec which can be used to set up the environment, called the LE and the exec VE. The last E in that word refers to that setting up of the environment. So, you have exec LE and exec VE which are used to set up a new environment. So, the new environment can be set up only when a new program is invoked using the exec call. So, on calling exec, the process can supply the environment for the new program, and these environment variables that are passed through the exec call will be passed to the next program, and it will replace the process current environment. So, when you are creating a new process using fork, the new process will inherit the environment from the parent process, and thereafter if it needs a new environment, then it needs to call the exec, which will be used to set the new environment. So, the environment variable mechanism custom tailors the operating system on a per process basis rather than being configured for the system as a whole. So, each and every process can have its own set of environment variables, can define its own set of environment variables, or can change its own set of environment variables. And next comes this process context. So, the next property of the process is this process context. So, what is meant by process context? This is the state of a running program at any point in time, and the state of the program, state of the running program will keep on changing, or the state of the process will keep on changing, and hence the context of the process also keeps on changing. So, the process context includes a number of things: scheduling context, accounting, file table, file system context, signal handler table, and virtual memory context. We will see each one of these, and we will see what each one of these refer to. So, what is meant by scheduling context? So, this is the information that the scheduler will need to suspend a process and restart the process. So, you all know that when a scheduler runs, so when scheduling needs to be done, the context of the old process has to be saved and the context of the new process has to be loaded. So, when a new process has been chosen to run next after the current process, then this new process, the context of a new process should be known so that it is loaded and it is run. So, this is called the scheduling context, and this would have contained all the saved copies of all the process registers, and it will have information about the scheduling priority. Each process has got a priority associated with it. So, if it is a high priority process, it has got a high scheduling priority that will be chosen for scheduling very quickly. If it has got a low priority, then it may not get the CPU or it may not be chosen for scheduling very quickly. So, each process is associated with a scheduling priority. Then we have information about any signals that are waiting to be delivered to the process. Signals can be sent to process, or signals or notifications that can be sent to process about some happening of an event, and or it can be sent from one process to the other, or it can be sent from the kernel to a process. And if there are signals that are pending which have to be notified for a particular process. So, the process has sent some signals, but the process has not received signals, they are all waiting to be notified to the process A, then this information also comprises or comes under this scheduling context. And then we have this kernel stack. So, what is this kernel stack? We learnt about something general called a stack. I told you that whenever there is a call to a function, a stack will be used, which will have information about the arguments to that function, the local variables in that function, and so on. But now, when a process runs in user mode, there is a different stack which is called the user stack. When the process runs in kernel mode, it uses yet another stack called the kernel stack. So, when it runs in kernel mode, when it is executing kernel functions or functions defined within the kernel code, then during that time the kernel stack is being used. So, it is used by the process while executing the kernel's code. And then you have accounting information. Accounting information about process which tell about the resources that are currently consumed by each process, and then it also has information about the total resources consumed by the process in its lifetime so far, and so on. So, currently that have been consumed, the resources can be which resources that use, maybe the CPU usage time. It can also have information about the amount of time the process spent in user mode, the amount of time the process spent in kernel mode, etc., and so on. So, all these information put together will form the resources that are consumed by each process. And then we have this file table. The file table will have an array of pointers to different kernel file structures. So, while making file IO system calls, process will refer to files using a file descriptor. We have seen earlier in a different module that whenever a file is created or whenever a file is opened, a return value is given which is called a file descriptor. And this file descriptor will be later used by every other system call which uses which is used to open, read, write or close files and so on. So, this FD is used by all these system calls, and when a file descriptor is given, this file descriptor is used as an index into this particular table which is called the file table. So, whenever you have a file descriptor, you use that FD or the file descriptor as an index into this file table to get the entry corresponding to that file that is currently being dealt with. And this entry in the file table will have pointers to other kernel file structures. And then you have something called a file system context. So, the file table will list the existing open files. If this file system context gives or applies to requests to open new files. So, you have a process has got a current root directory, it has got a current working directory, it has got a namespace all for its own, and all this information about the process is being stored in this file system context. So, the current root directory is specific for a particular process and that is stored in the file system context. It can also have information about the default directories to be used for new file searches, say the current working directory. All these are stored in this file system context. And then you have something called a signal handler table. I told you earlier that signals are used to notify certain events to processes. One process can notify an event to another process using signals, or the kernel can notify an event to the process using signals. So, whenever a signal is being sent to a process and say a process receives that particular signal, now what action needs to be taken for this signal? So, that action is being stored in a signal handler table. So, for all possible signals possible, whatever action need to be taken by this process is stored in the signal handler table for this particular process. In default or by default, the action is to terminate the process, but the process can choose to ignore the signal, or it can choose to execute or invoke another function or a routine which is defined in the process address space. So, the valid actions that are possible for a particular signal are to terminate the process, or to ignore the signal, or to execute a catch a function, or to execute a user defined routine which is defined in the process address space. And then we have this virtual memory context. So, the virtual memory context, it describes the contents of the process private address space. The address space of a process comprises of text, data and stack, as I told you earlier. So, all these fall into the virtual memory context. So, now that we have seen the different properties of a process, now we move on to see the difference between processes and threads. And Linux does not distinguish between a thread and a process as is being done in Unix systems. So, Linux looks at everything as a task. So, it uses the term task to define or to refer to a flow of control within a program. So, when I am looking at fork, when fork is called, fork will duplicate a process without loading a new executable image. There is another similar call which is called the clone. This also behaves very similar to fork, but this clone accepts a set of arguments, or it accepts a set of flags as arguments. These flags, depending on whether it is set or not, it will decide which resources are shared between the parent and the child. When you are using a fork, by default the child is going to get a copy of the parent, but or the resources of the parent are copied for the child process. But when you are using a clone, the arguments decide which resources need to be copied for the child process and which resources can be shared by the parent and the child. So, the flags that are possible, or the flags which can be given as arguments to this clone system call, are these clone fs, clone files, clone sighand and clone vm. Now, we will see what each one of these is. So, clone fs refers to the file system information. So, that gives you the current working directory and so on. So, if this clone fs is set, then this file system information is shared between the parent and the child. And if clone vm is set, then the same memory space is shared by the parent and the child. Say the text, data and stack is shared, the data will be shared by the parent as well as by the child. The text is shared by the parent as well as the child. And then you have this clone sighand. In this case, if this is set, then it means that the signal handlers are shared. And then you have clone files. Then if this is set, the set of open files is shared. So, if the parent had opened a set of files, and then if it creates the child process using this clone with this clone file set, then the parent and the child will share all the open files, the files that are already opened by the parent. So, now we see that the difference between the fork and clone is that in the case of clone, you can ask the parent or make the parent and the child to share some resources, and if no variable or no flag is set in the clone, then it behaves very similar to the fork system call. So, how is it possible to have this lack of distinction between a process and a thread? there is no distinction between a process and a thread. This is because the Linux does not hold the process entire context within the main process data structure. In the case of Unix, you have a data structure called the process structure, which holds all this information together. But in the Linux, it is not the case. The context is being stored within different subcontexts. So, as we saw earlier that we had seen about file system context, we saw about a file descriptor table, signal handler table, virtual memory context, and all these and so on, all these are held in separate data structures. And there is one common data structure called the task struct. It is a structure. So, that structure task struct will have a pointer to all these data structures. So, when you are using a clone with some variable set, then we know that which structure has to be shared and which need not be shared, for which you need to make a copy. So, if it can be shared, then you just have a pointer to that and you can share that particular structure maybe by incrementing some reference count. So, any number of processes can easily share a subcontext by just pointing to that subcontext and incrementing the reference count. So, the arguments to the clone actually will tell what subcontexts have to be copied and which to share. So, if you set some flags, then those have to be shared. If you do not set the flag, then those will have to be copied. So, by default a copy has to be made. If flags are set, then sharing can happen. So, any new process which you are creating will always be given a new identity and a new scheduling context. And according to the arguments passed, the kernel will share the subcontext data structures, or it will make a copy of the subcontext data structures. The fork system call, so we can say that is a special case of the clone system call, which will copy all the subcontexts, but it will not share any of the subcontexts. So, summary of this class is, we learnt what is meant by a process. We all know a process is a program in execution, and we saw how the process management is done in Linux. We learned that there are different process properties like the identity of a process. We learnt about credentials, we learnt about PID or process ID, we learnt about namespace, etc. and so on, and we learnt about the environment of a process. We saw two different vectors. One is the environment variables that have been given to the process, and the second is the arguments that are given to the process. And then we learnt about the context of a process. The context of a process comprises of the file table, the file system context, the virtual memory context, signal handler table, etc. and so on, all these kept in different data structures. And then we learnt about the difference between the fork and the clone call in Linux. In Linux, we use a clone call which lets you set different flags so that you can copy certain contexts and you can share certain contexts. So, if only copying is done, no sharing is being done, then that is a default case that happens as in fork. And if you want to set some flags and if you want to share some context, then you can use the clone call. References. Thank you.